let's get into this. All right, oxidation states. I love oxidation states. Okay, so oxidation state of tin in SnSO4 2-. Now, for oxidation states, there are several ways to do it. For polyatomic ions, I would recommend to be quick. If you know the charge of that ion, you can simply say the charge of that ion is the oxidation number of that ion. So we're asking for tin, so we don't care about sulfur and we don't care about oxygen. But we do know that SO4 is 2-. So the oxidation state is 2-. There are 2 of them, which means -4. That means tin is +4. Simple. And if we wanted to break it down, and we could say oxygen we know is -2. There's 4 of them, so that's -8 total. Then SO4 2- is a 2- charge. That means sulfur would have to be +6, and then we can figure out tin from there. But we don't have to. All right. Next, which of the following is not an assumption made by the ideal gas law? So the ideal gas law is PV equals nRT. I feel like this is lagging a little bit now. Here's what I'm going to do. I'm going to close the other window for exam 1. I guess I'll save these notes. I wish I was on my desktop. That's a little bit more power, but sometimes it doesn't catch the recording and it doesn't record any of the sound, which that would scare the shit out of me. So I don't want to do that. So I'm better be on my laptop. Okay, there we go. No lag. All right. So PV equals nRT. So gas molecules contain no mass. We know that they contain mass because oxygen gas is heavier than hydrogen gas. So that's not an assumption made by the ideal gas law. So that's true. Gases occupy no volume. We assume that the molecule's volume is negligible compared to the size between it. That's something that's in the notes a lot. So that's an assumption. Also, we have gas molecules do not experience intermolecular forces. This is true. We say that their collisions are elastic. They bounce off each other completely. And it's the same thing for D, is that they're elastic and they're constantly moving. We say all these things with the kinetic molecular theory of gases. So the correct answer is A. This is not a correct assumption. All right, which of the following is an oxidizing agent? Now, for oxidation and reduction, if something is being oxidized, the number goes up. If something is being reduced, the number goes down. And then the agent part of it is really the opposite. Just to be quick, is if something is being oxidized, it's the reducing agent. If something is being reduced, it's the oxidizing agent. So we're looking for something that's being reduced. That's really what this is asking for. Oxidizing agent means it is being reduced. So zinc by itself has an oxidation state of 0. Iron is going to be, so here we have nitrate is -1. There's 2 of them, -2. Iron is +2. This iron is by itself is 0. This zinc is now +2. And the nitrate again is -1. So we can say that zinc is going from 0 to +2. It's being oxidized. Therefore, it's the reducing agent. Iron is going from +2 to 0. It is being reduced. Therefore, it's the oxidizing agent. So the correct answer would be, what is the oxidizing agent? It would be the iron, but this iron is in the iron nitrate, meaning it is the aqueous iron 2+ ion. So the answer would be B. Okay, moving on. 4, a strong acid HA reacts with lithium hydroxide to form lithium with the anion plus water. So that's an acid-base reaction, similar to the combustion reactions. They have a predictable product. So it's acid plus base equals water plus salt. What is the net ionic reaction? So net ionic reaction, we have our HA, which is a strong acid. We know that. So it's H plus A-, dissociates completely, plus our lithium hydroxide, Li plus OH- yields Li plus A-, which is the anion and the lithium. They are dissociating because they're completely soluble, because anything with lithium is soluble. And then we have H2O as a liquid, which is a pure substance. So the net ionic equation, we can cross out everything in the complete ionic equation, which is true on the left and the right side. So we'd end up with simply water. So it'd be H plus OH minus equals H2O, liquid. And this is the case for all acid-base reactions for their, at least for strong acid, strong base, for their net ionic equation, it's simply just water. And you know the charge of A is negative because H plus will break off of this HA, and then A minus will be left over. If it was H2A, this is more of a Chem 2 question, you would have H plus and then HA minus. And then another hydrogen can come off. You'd have H plus and then A2 minus. So, you know, it could be different, but in this case, we just have simply HA. All right, next, a gas absorbs 30 kilojoules of energy as heat. All right, so automatically I'm looking at internal energy, delta E. So delta E equals Q plus W. Main thing to keep in mind, what is the sign of heat and work? And am I in kilojoules or joules, or what unit am I in? So we have absorption of 30 kilojoules of energy as heat. So absorbing, meaning heat, Q is positive. So Q is positive 30 kilojoules. W, so then undergoes an expansion, which does 50 kilojoules of work on the surroundings, meaning negative. So minus 50 kilojoules of work. So then we have Q plus W is 30 minus 50, so negative 20. So D is the answer. Okay, next. And yes, Samir, hydrogen is +1 on the periodic table. And that's why and then the oxidation state is always +1 as well for hydrogen. All right, so at STP, 10 grams of which gas has the smallest volume? So volume, we're talking about number of moles, right? Because according to the ideal gas law, volume is directly proportional, or sorry, inversely proportional. No, sorry, directly proportional. Directly proportional to number of moles. The more gas molecules you have, the more volume you have. So we can say that whichever of these gases is lighter, has a lower molar mass, that means that 10 grams of them will have the highest number of moles. That higher number of moles directly correlates to a larger volume. So we're looking for the one that has the smallest volume. Smallest volume means the smallest number of moles, which means the heaviest. So which one of these would be the heaviest? I think it would be CO2, because CO2 is 44, O2 is 32, N2 is 28, this is 17, and this is 18. So the answer would be CO2. For the one that will have the largest volume, it would be the NH3. Okay. Next, you have a balloon containing 0.25 moles of each of the following gases. Which of the gases will have the highest volume at STP? It's the same type of question, but we are fixing the amount of moles. So 0.25 moles of each one. Which one will have the highest volume? Well, what do we know about STP? We know that any molecule or any gas at STP is going to have a volume per mole. 1 mole is going to be equal to 22.4 liters. So 0.25 moles, doesn't matter what gas it is. If it's at STP, it's going to have the same volume. So we know that all these volumes would be the same because their moles are the same, right? And we don't care about their molar masses because each molecule, according to the ideal gas law, the molecular size, it doesn't matter because the distance between each molecule is so large. All right, next. When each of the solutions below are connected to a light bulb, in which solution would the bulb be the brightest? In other words, conduct the most current. So conduct the most current means which one is the strongest electrolyte? Electrolyte is an ion, has the most concentration and the highest concentration of ions. So what we can do is we're given concentration and we're given the compound. From the compound and the concentration, we can figure out the total ionic concentration. So for the first one, 0.5 times 4 ions, right? Fe is 1, and you have 3 chlorines. So 0.5 times 4 is 2.0. HCl, this is a strong acid. It will create 2 ions, 0.4 times 2, 0.8. For C, 1 molar times 3 ions. We have 2 nitrates and 1 magnesium. So that'd be 3.0 molar of ions total. Glucose does not break apart. This is a non-electrolyte, so we have no conductivity. And then for potassium sulfate, we have 3 ions of 0.5 each. So it would be 1.5. So the answer would be C, because you have the highest concentration of ions. 3 ions, and each one is at 1 molar. Next, consider a process where Q system equals P times delta V. Okay, now what do we know about this? So we know that E equals Q plus W. We also know that W equals negative P delta V. If E is 0, so the only way for this to be true, Q system equals P delta V, is if E is 0, you can move Q over, or you can move PV over, and you get Q equals P delta V. That's the only way for this to be possible. So off the bat, we can say delta E is equal to 0. So the system is not losing or gaining internal energy, but we can say that all the heat absorbed is used to perform work on the surroundings. That's one way to put it. Because if we have all the heat, so we have the work value is equal to the heat, right? So work is kind of equal to heat here. So we can say that all the heat absorbed is used to perform the work. And then that also means delta E is equal to 0, because there's no, that the Q plus W doesn't equal anything, because one is the opposite of the other. So, so this is basically saying Q equals P delta V is saying that Q equals negative W. That means all of the heat is being converted to work on the surroundings. Delta, or negative W, that's work on the surroundings. So yes, the system is neither losing or gaining energy, but simply the heat is being completely converted to work, which is going to the surroundings. That is a tough question if you're not familiar with how to manipulate Q plus W, but I hope that makes sense. All right, next, number 10. Which of these conditions and reasons best explains when a given amount of gas is likely to behave like an ideal gas? So, best explains when a given amount of gas is likely to behave. All right, so let's look at these. So at a high temperature, gas molecules move fast and can overcome intermolecular forces of attraction. So, yeah, I mean, if they overcome the intermolecular forces and there is no attraction at high speeds and high temperatures, then yeah, they will act completely elastically like ideal gases. 2, at low temperatures, gas molecules move slowly and can overcome intermolecular forces. So at low temperatures, they move slower, but this does not necessarily overcome their intermolecular forces. But if they overcome those forces, it will still be considered an ideal gas. Number 3, as at low pressure, the volume will be high. At low pressure, the volume will be high, and the gas molecules occupy less volume compared to the volume of the container. Yeah, kind of. So let's look at the number 4. So at high pressure, the volume will be lower, and the gas molecules will occupy more volume. So they can't occupy more volume than that of the container. So I would say 1 and 3 are the best answers for in which case do they best. So I don't like this question at all. So which condition and reason best explains when a given amount of gas is likely to behave? So I guess it's saying in which statement best describes the behavior of ideal gas. So if it's at high temperatures, the molecules move fast and they overcome the forces. That is true. If they move slow and they overcome the forces, that's still possible, but it's less likely. And for 3, at low pressure and high volume, the volume will be high, and the molecules will occupy less volume compared to the volume of the container. That's also true. So I'd say 1 and 3 is the best answer here. What is the molarity of a solution containing 4.5 grams of bromine dissolved in enough water to make 450 milliliters of solution. So we can simply find our molarity using our moles divided by our liters. So our liters, 0.45 liters on the bottom. Our moles, 4.5 grams of bromine. So bromine is the molar mass of bromine. If we go down to our periodic table, bromine is 79.9. So 79.9 times 2 is 159.8. Back here, so 4.5 divided by 159.8. That is 0.028. That's how many moles of bromine we have. Divided by 0.45, that's 0.0625, which is A. So a simple molarity. Find the moles, find the liters, divide the two. Okay. So given the following enthalpy of formations, determine which reaction is exothermic. Okay. So you can do products minus reactants for all of the answer choices. But the easier way is you can just kind of eyeball it and see which ones, and you kind of narrow some down. So as these enthalpy of formation values, you have 90, 33, and 9. So and then to figure out the enthalpy of formation of a reaction, it's simply products minus reactants. So for A, we're taking 2 times 90 minus the other two. The other two are smaller, so this is going to be a positive value, so it's going to be endothermic, not exothermic. Remember, exothermic is when enthalpy is negative. Endothermic is when enthalpy is positive for a reaction. So the next one, we have, and also the enthalpy of formation of O2, because O2 spontaneously forms, is going to be 0. That's why that value is not given here. So we have N2O, or NO2 here. So in the product, we have 33 times 2, that's 66, minus N2, another spontaneous one, it's a diatomic gas, it's going to be 0. So it would be 66 minus 0. That's going to be positive. For choice C, we have 9 minus, again, it would be 0 because these are diatomic gases. That would be positive. For D, 2 times NO2, which is 66, minus 9, still positive. So the answer has to be D, but we'll take a look and see why. We have 33 times 2, so that's 66. We have 0 here, and then we have 2NO, so that's going to be around 180. So 60 minus 180, that's going to be a negative number, and that's going to be exothermic. I can see why this problem was complicated, because if you didn't know that N2 and O2 were diatomic, and well, you should know they're diatomic gases, but their enthalpy of formation is actually 0, you wouldn't have got that right, or that would have been confusing. So yeah. All right. Number 13. So 10 kilojoules of heat is absorbed by 5 grams of each of the following substances. Which one is the greatest increase in temperature? Now, for specific heat capacity, the smaller the specific heat capacity constant, the quicker it will change temperature when given a certain amount of energy. So I'll say that again. Smaller specific heat capacity means it gains or loses temperature quicker. So for the best example I like to use with my class is sand versus water on the beach on a hot day. On a hot day, the water is not really going to change temperature because it has a high specific heat. It requires 4 joules per gram to change by 1 degree. Meanwhile, sand only takes 0.84 joules to change by 1 gram, or per gram to change by 1 degree. So we're looking for 5 grams of each of the following substances. Which one would experience the greatest increase in temperature? This means whichever one has the smallest heat capacity of these, it is silver at 0.23. Or no, sorry, nope, that is wrong. It is lead at 0.12. Yeah, thank you, Robin. All right, good. So the smallest one means it will increase in temperature the most. All right, number 14, almost halfway done. Yes, correct. That is correct. So if the substance has a smaller heat capacity, that means it changes temperature the quickest and the most. All right, number 14. A gas bottle contains, or a gas bottle, yeah, gas bottle, bottle of gas, a gas bottle contains 0.25 moles of gas at 730 mmHg. If the final pressure is 1.15 atm, how many moles of gas were added to the bottle? So moles of gas, I'm automatically thinking pivnert. Whenever you see moles, you think pivnert and RT. So we have two states. We have pivnert initial and pivnert final. We're at constant volume and temperature. So we can say volume is constant, so we can get rid of that. Temperature is constant. So we have really pressure in moles. So we can say that, all right, the pressure divided, and also R is a constant. So pressure divided by moles. This isn't a law, but we can use the ideal gas law to figure this out. So the ratio between pressure and moles at the start and pressure and moles at the finish is a constant because of pivnert. So the initial pressure is 730. Now we're given the conversion that 730 is mmHg, and we know that 760 mmHg is 1 atm. If we divide 730 by 760, we get 0.96 at atm. So 0.96 divided by 0.25, which is your initial moles. We're being asked for, if the final pressure is 1.15, how many moles were added? Okay, so we can find X. Let's find X first. So what we can say is that, and correct, we could also use the, well, no, we cannot use that law. We cannot use the combined gas law because that does not involve moles. So if we solve for this, we get 1.15 times 0.25 divided by 0.96 gives us X equals 0.299. Now, if you look, that is one of the answer choices, which I probably threw off a few of you. 0.299 moles is the final amount of moles. But the question's asking for how many moles of gas were added to the bottle. So we would take that 0.299 minus 0.25. And we get 0.493. Yeah. Okay, good. That one's a little bit, you have to think about it because you have to think about it because we're not using one of the conventional laws that we learned during class. But if you start from the ideal gas law and the concept that I teach my class at least, if there are moles of gases involved, write down pivnert and worry about it later. Exactly, it can be manipulated. So if you write down pivnert and start with that, you start looking at it and say, all right, constant volume and temperature, I know I can cross those off. And you end up with that relationship between pressure and moles, which that's what the question's asking for. All right, next. So an expanding gas does 17.5 kilojoules of work on the surroundings. All right, so we know that work equals negative 17.5 kilojoules because it's going on the surroundings at a constant pressure of 5.55. If the gas initially occupied the volume of, that's a weird looking V is 12.5 liters. What is the final volume of the gas? Okay, so we know that work equals negative P delta V. And the work is given to us in kilojoules. Now, with this equation, I warned my class, and you should have been warned that the negative P delta V does not give you kilojoules, even though we normally express work in joules and kilojoules. It gives you liters times ATM because pressure is in ATM and delta V is in liters. So we need to make that conversion from kilojoules to liter ATM to make this equation work. We're given negative 17.5 kilojoules. So if we take that, so we can do times 10 to the third joules times 1 divided by 101.3 joules, and this is going to be liter times ATM, we can come up with our conversion. So or our liter ATM. So 17,500 divided by 101.3, that is 172.8 liter ATM. So this 172.8 liter ATM is simply converting the 17.5 kilojoules to liter ATM. Now this will equal, this is negative, of course, so negative equals negative P delta V. So negative 5.55 times delta V, which is final minus initial. So the final volume we don't know. So V final minus V initial, which is 12.5. So 12.5. You can't see that part. So then we can solve for V final, and I'll write it again down here. So negative, so negative equals negative, so we can make it positive. So 172.8 equals 5.55, which is your P, times your delta V, which is V final, minus V initial, which is given, which is 12.5. And then we're looking 5, and then we can solve and figure that out. So anybody want to solve it? Yeah, it's an algebraic expression. So anybody want to solve it real quick? I'm getting lazy. I'll go on to 16, and then someone put in the chat what the answer is. Okay, so a mixture. So number 16, 44. Okay, you got 44. Thank you so much. Oh, we got 19. We got 44. What do we got? We either 19. Okay, so maybe we should figure it out. 44, it's B. Okay, so maybe whoever got 19, you maybe did something wrong in the calculator, but I think the consensus is 44. All right. All right, so number 16. A mixture of 0.22 moles of CO, 0.35 moles of H2, 0.64 moles of HE has a total pressure of 2.95. What is the pressure of H2? So we're looking for partial pressure. Now, for partial pressure, we know that the partial pressures add up to the total pressure. And it's related to the mole fraction. So if we figure out the mole fraction of H2 and multiply that mole fraction by the total pressure, we get the pressure fraction. So the mole fraction, another way to say it, the mole fraction is the same as the pressure fraction because we consider each molecule of gas as equal, independent of the mass of it, because the distance between each molecule is so large. So let's look at H2. We have 0.35 moles divided by the total number of moles in the sample, which is 0.35 plus 0.22 plus 0.64. And that's going to be 1.21. So 0.35 divided by 1.21 gives us the mole fraction, which is also the pressure fraction, 0.289. We take that 0.289, multiply it by the total pressure of the sample, 2.95, and we get 0.853 ATM. And the answer is B. Okay, next. Which of the following solutions will have the highest concentration of bromide? All right, this one's not too bad, just like the question we saw before. A will have 0.2 molar times 1 bromide, so that's 0.2 molar bromide. For B, we'll have 2 bromides and 0.1 each, so that's again 0.2 of bromide. For C, we have 2 bromides and 0.12 each, so 0.24 of bromide. D has 1 bromide, but it's 0.25, so 0.25 bromide. And then E has 3 bromides at 0.1 each, 0.3 bromide, so the answer is E. Okay. Next, how many of the following compounds are soluble in water? All right, now for those of you who are not in my class, I'm not sure how your instructor taught solubility rules. There's a big chart. It is tough to memorize the big chart, and you probably don't want to memorize the big chart. So an easy way to get around that and to still get probably 90% of the answers right is you remember 3 rules. Rule number 1, group 1A always soluble. And also you can add ammonium to that, because even though it's not in group 1A, it still has a lot of the same properties. It's +1 and it behaves similarly. So these are potassiums, sodiums, and more, and everything else, lithium. So these are always going to be soluble. The second rule, nitrates and acetates, always soluble. The third rule, we have 3 ions that are not soluble: silver, lead, mercury. May not be soluble unless they're with soluble, unless they're with group 1A, or sorry, unless they're with nitrates or acetates. So using those 3 rules, you can bypass a lot of the other rules. And here's an example. Let's look at how many of the following compounds are soluble. Lead with an hydroxide. Well, lead tends to not be soluble unless it's with an acetate or a nitrate. In this case, it's not, so it's not soluble. Lithium nitrate, super soluble. Lithiums are always soluble. Nitrates are always soluble. And the second rule is nitrates and acetates are always soluble. So here we go. Lithium nitrate, always soluble. So that's 1 that's soluble in water. Ammonium, always soluble, right? So group 1As and also ammonium, always soluble. So another one that's soluble. Potassium, group 1A, soluble. So how many of the following compounds are soluble? 3. So just knowing those 3 rules, you can boil down, you can narrow it down to, even in a tough question, maybe you'll narrow it down to 2 answer choices and you have to guess. But in 90% of the questions from teaching this course for 6 years now, these are the 3 rules that it all boils down to, for the most part. And if you get one on the ACS that is like one of these nuanced examples, then whatever, kill me. But trust me, that'll save you a lot of studying. All right, next. How much of a 0.35 molar solution is needed to make 0.1 molar with a volume of 3.5? So this is dilution. M1V1 equals M2V2. So your M1 is 0.35, and we're diluting it. So we don't know how much volume we need, but we know how much volume we're going to make. And we're making a 0.11 molar, and we want that volume to be 3.5. So we need to figure out how much volume we need to do that. So 0.11 times 3.5 divided by 3, I messed that up. 0.11 times 3.5 divided by 0.35 is 1.1. So the answer would be C, 1.1. Next, using the graph below, determine which of the following statements below is incorrect for the 4 different noble gases at a given temperature. All right, so all gases have the same average kinetic energy. Because remember, kinetic energy is 1/2 mv squared. Their masses and velocities are inverses of each other, meaning if you have a heavier one, such as krypton, it will move slower than helium. So mass and volume are inverses. So that means, but they all balance out, meaning the average kinetic energy are the same. So which of the following is incorrect? So we know that A is correct, so that's not the answer. For B, gases have the same velocity. That's incorrect, because we know that the slower ones are heavier and the lighter ones move faster. So we know that helium moves faster than krypton because it's lighter. So this one is correct, or this one's incorrect. So that might be one of the answers. C, the gases have the same density. That's not true, because we know per molecule, the heavier ones will have a larger density because it's grams per volume, right? Grams per centimeter cubed. So for the same number of atoms, it'll weigh more. So we know that the densities are not the same. So the answer would be B and C, which is represented by answer choice E. Good. All right, next, part B. So a 21.8 gram sample of ethanol is burned in a bomb calorimeter according to the following reaction. How much energy is released when this sample is burned? The molar mass of ethanol is 46.07. All right. So it tells us that this reaction, so in the way this is written, the reaction here, the delta H, it releases the combustion, it releases 1200 kilojoules. We're being asked, if this reaction releases 1200, how much is released by 21 grams? That's it. So we first need to figure out how many moles we're talking about here. In the reaction that is balanced, 1 mole of ethanol is responsible for the release of 1200. So we're trying to answer how much is released for 21 grams, or however many moles that is, which we can easily find out. 21.8 grams divided by 46.07 grams per mole, which is given to us. And even if it's not given to us, we can find it on the periodic table using the formula. This is equal to 0.473 moles. So our sample is 0.47 moles. We know that from the given information, 1 mole is negative 1235. So we multiply this by negative 1235, and we get 584. So negative 584. That's E. That's it. Ta-da. That's not so bad. All right, number 22. A 1.52 gram sample of an unknown pure gas occupies a volume of, I think this one had a problem. It's the one that had an issue in the exam, but we'll do it anyway. So the sample of a gas had a volume of 0.335 and a pressure of 1 atm, and temperature of 100. What's the unknown gas? So you have grams and you have a lot of variables given, so I'm thinking piv nerd off the bat. PV equals nRT. Pressure, 1 atm. Volume, 0.335. Whenever these questions come up of what is the identity of the gas, they're going to be piv nerd every time. And you need to figure out moles first, because we can break down moles into, we know that grams per mole. So we know that the molar mass is grams per mole. So we can figure out, if we figure out moles, we have grams, we take grams divided by n, that equals the molar mass. So we can figure that out. But first, let's find moles. So we know this is equal to n times 0.08206 times our temperature in Kelvin. Remember Kelvin, this would be 373 Kelvin. So then we can divide this. So we do 0.08206 times 373. That's 30.6 times n equals 0.335. So 0.335 divided by 30.6. That is n equals 0.0109. This is n. We have the grams. The grams is 1.52 divided by the moles, 0.0109. So 1.52 divided by 0.0019. That equals 139. This is the problem that we had during the exam. 139.4 grams per mole. And there's none of these gases are 139.4 grams per mole. And let's see, krypton is 83, xenon is 131. So I guess I don't really check the 125 exams. I do more the 126 this semester, but whoever did this question, maybe the math was a little bit off. But we told you guys during the exam to do xenon, which is 131. So that's closer to 139. Yeah. So the answer would be we told you to put xenon. Okay. Next, number 23. What is the mass of barium sulfate with a molar mass of 233 is produced when this much of barium chloride is mixed with this much of iron sulfate? All right. So there's a lot going on here. Let's write the equation first. If we're being asked for how much is produced when we add this and it makes this, write a reaction. That helps you the best. So we are adding barium chloride. And this is why it's important to know how to write the formulas for these molecules, because if you're just given the words and you don't know how to convert it, then you won't get it right. So BaCl2 is mixed with iron 3 sulfate. So plus iron 3 sulfate would be Fe2SO4 3. Because sulfate is a 2 minus, there's 3 of them, this means -6. Each iron will have to be +3. And then once we find the products, it would be barium sulfate. So BaSO4 plus each iron is +3, so it would be FeCl3. Now we have to balance it. So if there's one barium there, 2 chlorines, 3 chlorines, so a 2 would have to go there, 3 would have to go there. Now the bariums are not balanced, so 3 bariums here, we have to put a 3 here, and we're done. So you see that, for those of you who are not in my class and don't balance it that way, you see how easy that was? And that's a rather complex one to balance. So just by going left to right, looking at each atom to each atom, left to right, and comparing them and putting the correct coefficient will get you the right answer quickly. So let's look at the question now. So where's the mass of barium sulfate? That's right here. Is produced when this much of barium chloride is mixed with that much of iron sulfate. So we first need to figure out the moles of everything. So it's produced when this is the barium chloride. So 0. It's too thick. Let's see. 0.150 molar of barium chloride equals X divided by 0.125 liters. We can find the moles. 0.125 times 0.15 is 0.01875 moles. Okay. And we're mixing that with the same amount. Okay, the same amount of the iron 3 sulfate. That's good. So we don't have to do more math. So we have 0.01875 of both reactants. So now, just like exam 1, we have to do some limiting reactant here to figure out what we're doing. So I found this moles from using the molarity and the volume of the reactants. So they both are 0.15 molar, and their volume is 125 milliliters. So I set this up in the molarity equation to figure out their moles. And since they're both the same, they have the same number of moles. Now, to figure out which one's limiting, we can say, all right, if we have the same number of each reactant, and let's compare them to the barium sulfate. Barium chloride, it's a 3-to-3 or a 1-to-1. The barium chloride will make 0.01875 moles of product of barium sulfate. The iron 3 sulfate, it's a 1-to-3. So the iron 3 sulfate will actually create 3 times that, which is 0.056 moles of barium sulfate. So that means the barium chloride, I messed up. The barium chloride is going to be the limiting reactant, and it creates this much of barium sulfate. So this should kind of be review from exam 1 at this point, just finding limiting reactant. But now that we know the limiting reactant and how much of the barium sulfate it produces, we simply multiply that number of moles by the molar mass of barium sulfate, which is actually given 0.01875 times the molar mass that's given, which is 233, and that gives us 4.37, which is E. So that one, it's simple, but it does take a while because we first need to recap it, we first need to balance the equation, which that's one difficult step for some. Then we need to see, all right, how many moles of each reactant do we have? Luckily, they're the same, so we don't have to do 2 steps of math. Then we have to see, all right, how much barium sulfate does each reactant make if it were to react to completion? Based on that, whichever one creates the least amount of moles of product of barium sulfate is limiting, and we can say that is the amount of barium sulfate that is produced. We can multiply that by the molar mass of barium sulfate to come up with the grams of barium sulfate. All right, next, number 24. If you're given an overall reaction and we have 3 steps, what is delta H for the reaction 2? All right, I love Hess's law. So for those of you who know me, you know I love Hess's law. This is a Hess's law problem where we want to manipulate these equations to make them look like the overall equation. Easy way to do this is to section off each reactant and product and do one at a time systematically. So I like to look at first one, CS2 in the overall. Where is CS2 in the mechanism? Right here. We want one of them on the left. We have one of them on the right. That means this reaction needs to be flipped. So we have the new reaction is CS2 yields C plus 2S. And then our delta H is also flipped, meaning it is negative 87.9. Okay, next, 2O2. Where is O2? O2 is in several places, reaction 1 and reaction 2. I'm going to leave it alone. Whenever you have a reactant or a product that comes up a couple times, you leave it alone and it'll work out at the end. Next, we have CO2. There's CO2 on the right. We want one of them on the right, and we have that right here. So we're going to ignore, we're not going to change this equation at all. So that one's good. So next we have, in the product, we have 2 SO2. Reaction 2 has 1 SO2. So we need to multiply this by 2. So we have 2S plus 2O2 yields 2SO2. And then our delta H is going to be equal to X times 2, or 2X. All right. Since this delta H we're looking for is the delta H for this reaction itself, we multiplied reaction 2 by 2, which means the delta H that we're going to find is actually 2 times the delta H that we're looking for, which is why I have 2X. So next, we're going to simply add these together, add up all the reaction mechanisms, and they will equal the delta H for the total. And normally in Hess's law, we don't have the delta H final. We only have the delta H's for each step. But in this case, we just have to find the delta H for one of the middle steps by knowing the last step. So let's add these all together. So reaction 1 is going to be negative 393.5. Reaction 2 plus 2x. Reaction 3 minus 87.9. That's going to equal the total, negative 1,075. That should be a 1. Okay, so let's figure this out. 1,075. 1,075 minus, that's going to be plus 87.9 plus 393.5 divided by 2. I got negative 296.8. So X equals negative 296.8, which is E. I love Hess's law. It's a really good question. And no, I didn't come up with that one. I wish I did. Next. So according to the following thermochemical equation, what mass of H2O must form in order to produce 975 kilojoules of energy? Okay. So this one's not too bad. Just molar ratios and analysis. Well, not really molar ratios, just dimensional analysis. So let's look at this reaction. And we're focusing ourselves on H2O. In this reaction, H2O is in the product. 2 moles of them create negative 184. So if 2 moles create negative 184, then X creates negative 975. So that's what we're figuring out, because we're looking for the amount of H2O in order to produce or release 975. So all we have to do is figure out that ratio. So 2 divided by 185 times 975 is 10.5. So that's 10.5 moles, not grams, moles. It's asking for what mass of H2O. This gives us the moles of H2O because we cannot, it's better to use molar ratios, not mass ratios, because with the same compound, yeah, you can use mass ratios, but if you're looking from compound to compound in a chemical reaction, we can't do that. So 10.5 moles times the molar mass of water, which is 18, that gives us 189.7. Maybe I rounded wrong, but it should be 191. So close enough. Maybe I rounded wrong, but that's the answer. And let's think about it. Does that make sense? So two moles of water is 36 grams. 36 grams releases 184. Almost 1,000 grams is 5 times that. So 36 times 5 is around 180. So yeah, 191 makes sense. All right, look at number 26. So calculate the enthalpy of the oxidation of ammonia in a given formation. So we have enthalpy of formations for everything. And we're being asked to calculate the enthalpy of formation for the total reaction. So we're taking products minus reactants. So in the essence of time, I'm not going to figure out the answer, but you guys are more than welcome to. And you can put it in the chat, but I'll walk you through the formula. So products, 4 times NO. So NO is 90.3. So 4 times 90.3 plus 6 times water. Water is negative 241.8. That whole thing is the products minus the reactants. Reactants is 4 times NH3, which is negative 46.1. That should be times negative 46.1. I messed up. Oh, what did I do? Okay, so let me just erase. I just wrote it weird. All right, so okay, let's see. Now my cat is trying to bite the pen as I'm writing, so that's another. Expect the unexpected. So 4 times the NH3, so that's negative 46.1, plus another reactant, which is 5 times the O2. And O2 has no enthalpy of formation, so it's 0. So plus 0, and then you can solve that, and that would equal the enthalpy of formation for the whole thing. So yeah, if you guys want to put that in the chat, that'll be great. But otherwise, I'll keep going. Oh, A, nice. Okay, so we got A. Hopefully, the consensus is A. Thank you, guys. I'm glad someone's still listening. All right, next, number 27. So we have 50 grams of iron with the specific heat capacity is heated with a flame and is cooled down in a 650 milliliters of water. If the initial temperature of the water was 25 and the final temperature was 27 after thermal equilibrium, then what was the initial temperature of the iron? All right, now this we are using Q equals MCAT. Q equals MC delta T. Now this is the simple lab experiment of heating up a piece of metal, putting it into water, and determining what metal it is by how fast it cools off and what's the temperature of the final temperature of the water. So we can basically make 2 Q equals MCATs equal to each other, one for the metal, one for the water. So let's do that. So we'll do metal equals water. So M of the metal is 50. So 50 grams of iron times C of the metal is 0.5 or 451 times delta T of the metal, which is what we're trying to figure out. We're trying to figure out the initial temperature of the water. So the final temperature of the water, or sorry, of the metal, is 27.6 because that is when thermal equilibrium is reached, meaning both the water and the metal are 27.6. But this is a delta T for the metal. So minus the initial, T initial, close parenthesis, equals the Q equals MC delta T for the water. So it is 650 milliliters of water. That's equal to 650 grams because it's a 1 gram per milliliter, times 4.184, which is your specific heat capacity of water, times your delta T. In this case, the delta T is given. It is 27.6, which is your final, minus your initial, which is 25. So the delta T is 2.6. And we can solve this. So I'm going to need your guys' help again. If you guys want to solve for T initial here, basically all we did was we made an MC delta T for the metal and make it equal to MC delta T of the water. And the reason why we can do that is because the heat, and we're assuming here that the heat is not dispersed into the surroundings, but the heat is being directly converted from all the heat of the metal is being transferred to the water. And that's why we can say that the temperature final and temperature initials, or the temperature finals, are the same at thermal equilibrium, and our Q values from the Q, or the heat leaving the metal, is the same as the heat being gained by the water. So that's why we can say that they're equal to each other. And then, so if you can find that T initial, I'll just keep going. And I'll fill it in as someone gets the answer. All right, next. The reaction below is run with 1.5 moles of sodium sulfite and an excess of HCl. So we already know sodium sulfite is the limiting reactant. It produces, and the product gas is collected over water. What is the final volume of the product gas? If the total pressure is 770 mmHg and the temperature is 35 Celsius, assume the vapor of the water is negligible. So it makes more sense. It should be hot. You're good. You're good. No problem. Okay. So in this case, we have, where's the final volume? So we have 1.5 moles of the sodium sulfite. This is sodium sulfite, Na2SO3. So 1.5 moles. And we're collecting the gas over water. The only gas in this reaction in the product is SO2. So it's a 1-to-1 ratio. So this creates 1.5 moles of SO2. So what is the final volume of the product gas if the total pressure is 770? So 770 divided by 760, which would give us our ATM. 770 divided by 760, that's 1.01 ATM. And a temperature of 35. So temperature is, let's see, 35 plus 273. That's 308 Kelvin. All right. So I think there's some confusion for 27. You can, so to make this work, you can make this negative because the energy change, or the heat change, if one is losing heat, so the metal would be losing heat to the water. So the positive of one equals the negative of the other. So if you solve that, you'll probably get the 341. Because if you leave it up as straight as, the TI would be negative. So, but we can go over that again later after we finish this. All right. So next we have, we can use PIVNERT. PV equals nRT. And we can figure out that what is the final volume of the product gas if the total pressure is 770. So total pressure 770. We have to look at the reaction to see, to make sure SO2 is the only gas. And it is. If it wasn't the only gas, we might have other gases to consider to find the total pressure. But we don't have to, which is good. So our pressure is going to be 0.01 or 1.01 times our volume, which is volume. Oh, we're trying to figure that out. So volume, then that equals 1.5 moles times 0.08206 times temperature, which is 308. So then we can figure this out. We get 1.5 times 0.0206 times 308 divided by 1.01. And that equals volume of 37.5, and we have 37. So that's the answer. So, okay, so B is the answer for 28. All right, almost done. 29. So a gas expands against an external pressure of 4.5, which results in a piston of an area of 15 decimeters squared to be displaced 5 decimeters. How much work did the gas perform in joules? So work equals negative P delta V. Okay. So we have an external pressure of 4.5. The question is, what is our change in volume? So we have a piston. So a piston looks like this, right? So and it's going to move. This piston is the cylinder, and you have a circle in the cylinder that will move up, and there's pressure down here. So there's a pressure. So we're saying the pressure is 4.5, but the pressure of the 4.5 is actually up here. It's an external pressure, and the piston's moving against that pressure. And this results in the piston, which this circle has a surface area or an area of 15 decimeters cubed or squared to be displaced 5 decimeters. So that means this distance is 5 decimeters. So to figure out the volume, simply just volume of a cylinder is the surface area of the cylinder times the height. So it would be 15 times 5. So that would be 15 times 5, and that's 75 cubic decimeters. And what we know is that 1 decimeter is equal to 1 liter. So we know that 75 decimeters cubed, 1 decimeter cubed is equal to 1 liter. So 75 decimeters is equal to 75 liters. So we can say that the volume is just 75 liters. So negative 4.5 atm for the pressure. This moves the piston 75 liters. Okay. Sorry, something important. Okay, so then this is going to equal our work. So our work would be 4.5 times 75, which is, so work equals negative 337.5. This is going to be liter ATM. And we know that 1 liter ATM is 101.3 joules. So we need to multiply this by 101.3. 101.3. So that's going to be 34,188.75. And that's going to be 34,000 joules. It's going to be negative. So how much work did the gas perform? So it's around negative 34,000. Cool. All right. All right. Finally, let's get to the last one. All right. So in a fixed volume container, 2 moles of N2 undergoes a reaction with 5 moles of H2 according to the unbalanced reaction. Now, this was a problem on the exam too. This unbalanced reaction was actually balanced. So let's just take that out. Because if we look at this, it's pretty balanced to me. With total pressure of 1.5 atm. After the reaction complete, what is the total pressure inside the container? So in this case, we have a reaction that has all gases, and it has a total pressure of 1.5 atm to start out with. And we're asked for what is the total pressure after the reaction is completed. So here's what we need to figure out. We need to go through another limiting reactant problem, find out how much is produced and how much of each gas is left over. Then we can figure out what is the total pressure of the new system. So we have 2 moles of N2 with 5 moles. So I'm going to write the reaction again. So N2 plus 3H2 yields 2NH3. So we have 2 moles of N2, 5 moles of H2. So if we're reacting this, we have 2 moles of N2. It's a 1-to-2 ratio. So the N2, the 2 N2s would create, it's a 1-to-2, so it would create 4 moles of NH3. Then our 5 moles of H3, or sorry, of H2, since it's a 3-to-2, it would create 3 divided by 2 times 5. It'll create 7.5 of NH3. So our limiting reactant is the one that will create the least. So that's this one. So we know that the total pressure to start out with is 1.5 atm. So we can say that based on the mole fraction, we can figure out the partial pressure of each of the reactants. So for N2, 2 divided by 7. So keep in mind, we have 2 moles of N2. The total number of moles with all the reactants is 2 plus 5, which is 7. So 2 divided by 7 is 0.28. Multiply that by 1.5, and that gives you the partial pressure to start out with of N2, which is 0.42 partial pressure. Same thing for H2. 5 divided by 7 is 0.71 times 1.5 is your total pressure, which equals 1.07 atm. Okay, so based on those pressures, we don't even have to use the moles. We can use the pressures directly to figure out how much atm is left over for each reactant. But we know that N2 is limiting, so the N2 completely goes away. It will create, since we have 0.42 atm, and the ratio is a 1 to 2, so it will create. So if we try to find the limiting reactant this time using the pressure, right? What will happen? Sorry about that. So for N2, we'll have 0.42 will create. It's a 1 to 2. It'll create 0.84 for the N2. For the H2, we start at 1.07. 1.07 atm will create what now? So it's a 3 to 2 ratio from H2 to N2. So 1.07 times 2 divided by 3 is actually 0.71. So I was wrong. The H2 is the limiting reactant. H2 is limiting. That means all of the H2 will be used up to create 0.71 of the product. If that's the case, we can go backwards to see how much N2 was used up. So doing that process and going backwards, we can see that 0.71, it's a 2 to 1 ratio going from the NH3 to the N2. So if 2 makes 1, 0.71 was made by 0.355. So what that means is that we started out with 0.42. We used 0.355. So if we subtract those two values, 0.42 minus 0.355, 0.42 minus 0.355, we get 0.065 atm. So the answer to the question, finally, is what is the total pressure after the reaction is completed? So we would take the product pressure, 0.71, and add it to 0.065.